Hi, welcome. This is the 15th lecture on topology. Today we are going to concentrate on an important basic notion, namely a base or basis for a given topology. So we start with a topological space, that is a set with a topology. Then we are looking for what is known as a basis. Okay. In the second one we will do something else, but let's stick to that. So our basic idea, okay, let's get started. Yeah, so let us recall how we built a topology. Suppose XD is a metric space. Okay, how did you define the topology of open sets? Okay, the building blocks here were the open bars where X is in X and R is positive, and using that we built a tau, right? When did you say U is in tau? If for every X in U there exists an X in X, there is an R positive, so that BXR is contained in U. Okay, that means U is going to be union of some BX RX where X is in U. This R may depend upon R or RX, so we call it RX. Yeah, so we want to generalize this notion. Okay, so let us start with a topological space X tau. Okay, and let me look at a collection B, a sub-collection. Okay, this is a collection, so it's a collection of open set, may not be all of tau. Okay, may not be all open sets. Then I say B is a basis for the topology tau if, okay, for any open set U in tau and for any X in U, I can find a B in script B so that X belong to B and B is contained in U. Do you see the similarity? How we define the topology of open sets on a metric space? It's something like that. Yeah. So one usually says, again, this lets us focus. Okay. The standard way of writing will be, they will say if, okay, every tau open set is the union of a sub-collection B dash of B. Okay, you start with a sub-collection and then you say U equal to union B and B in the sub-collection. Okay, this is pretty easy to say, but then when I want to show something is a basis, this tells me what I have to do. It lets me focus on the problem. I have to start with an arbitrary open set and take some arbitrary element in that, then I have to find a B. This B may depend upon BX. X, so we call it BX. You understand? So what are the examples? Let us look at a lot of examples. The first example is if XD is a metric space and tau D is the metric topology on X. Then what is our collection B? This is all B X R, so that X is in X and R is positive. Okay, this is a basis. Okay, you should not just take my word for granted, you should actually prove that. Okay, because that's how we define. When I say U belong to tau D, what does it mean? Give me any X in U, then there is R positive, so that BXR is contained in U, but X actually in BXR, therefore we have shown that this is a basis. Okay, pause, review, proceed. This is the first most natural example. Second example, it's a very special example, but let us look at that. See, the basis may not be unique. You understand? For example, I can think of another basis. Okay, Okay, this is another basis. I'm using the same symbol. If you want, you can call it B2 or B. Okay, let us say B1. This consists of all Bx 1 by n, and said that x is in capital X and n is a natural number. How many of you can see this is a basis? How many of you can see that? Because let U be open in the metric topology, and since this is open, what do I know? There, okay, given any x, given x in U, I know there is an R positive, so that Bxr is contained in U, right? But let's look at this is 0, this is R, right? This R is positive. Therefore, do you remember? Again, don't. I will use analysis. There is an Archimedean property. Tells us there exists a natural number n, so that 1 by n is less than R. That is, R is greater than 1 by n, which is same as saying if you want n R is greater than 1. Yeah. Okay. Therefore, if I look at Bx 1 by n, right, this is contained in Bxr, and this is contained in U, and x belong to this. So this fellow belong to B1, right? Therefore, if to show B1 is a basis, what should I do? You gave me an open set U in tau d, and then x in this. Then I have to find B in B1, so that this is contained in U. Have I done that? Yes. Therefore, B1 is a basis. Okay. Paul, review, proceed. Alright, let's look at yet another special case. Okay, now take x equal to R with the standard metric space. So, standard metric, distance metric, okay, absolute value metric. Then what does it say? Then I have my B1. Okay, right? Okay, let us look at. Okay, so this B is the standard collection AB, AB in R, and A less than B. Okay, this is a basis. But this is actually cheating, because if you looked at my, if you watch my metric space thing, I would have shown this is nothing other than BC, okay, B minus A by 2, where C is the midpoint, A plus B by 2, right? So I have AB and take the midpoint C, and this is B minus A by 2, okay. Therefore, this is nothing other than the original our metric space collection. Think of this RD with the metric space. This is nothing other than the collection BXR. Yeah, and therefore I can think of again a B1, which is collection Bx 1 by n, okay, x in R and n in natural number. But this is a fancy way of writing, but this simply says look at x minus 1 by n, x plus 1 by n, and this collection of all elements as n in n. So these are all special cases of what you have seen in the metric space, right? But in the case of real numbers, I have another interesting example, call it B2. This is set of all x minus 1 by n, x plus 1 by n, okay, where x is only rationals and n is a natural number. Maybe I should start with x in R first, then I will come to, oh, this is what I just now did. Yeah, no, what I meant is, sorry, no, what I meant is this. X minus R, x plus R, as x is in Q, but R is positive. Okay, this is what I wanted. I wrote something wrongly. Do you understand that? So the centers of the balls are only rational numbers, not any real number. Okay, So the right, is this collection is B to a basis for the usual topology on or the topology on or what is that I have to do? Okay, so you give me a real number A in R. Sorry, let us take U to be an open set in R. Okay, U in tau D, and let's fix an A in U, right? Therefore, what do I know? I know that there is a R positive, so that A minus R to A plus R is contained in U. So let us look at this. This is my A minus R to A plus R is contained in U. Do you understand this? Yeah, right. Now what is that I want? So this is given, but what I want is, I want to say there exists a rational number x in Q and some epsilon positive, so that my A belong to x minus epsilon by x plus epsilon, and that is contained in U. This is what I want to show. If I want to show B2 is a basis, what is that I have to do? Give me any open set and give me any point there. I have to find such a thing, right? So how do you think I can do that? Yeah, one you quickly says, the teacher will say it's the density of rationals. Okay, this is a mantra. Okay, but this is what I call mere paas mom hai kind of argument. Okay, it doesn't explain everything. You have to work on this, right? So what does this mean? So if I have, let us say, x, and I want to put my x minus epsilon to x plus epsilon, I want my A to be somewhere here. How do I do that? So this is same as saying, notice that this is same as saying mod x minus A is less than epsilon, right? Yeah, okay. So what does this mean then? This is same as saying, can somebody guess? Mod x minus A is less than epsilon. That means the distance from A to x is less than epsilon, right? Are you following? So I have A and A minus epsilon to A plus epsilon. So there exists x and q. Now do I know that? Okay, this is same as saying this, right? So I want to find a rational number in the interval A minus epsilon to A plus epsilon, but that's exactly density of rationals. Density of rationals says, given any two real numbers A less than B, there is a rational number R, so that A is less than R less than B, right? So from that it follows. Yeah, please pause, review, proceed. So this is B2, right? Yeah. Are you following what I said? I'm slightly worried. See, suppose my x is somewhere here, okay, then this distance is less than epsilon. Therefore, if I take x minus epsilon to x plus epsilon, yeah, my A will be contained in that. Because distance between x and A, or x may be here also, don't worry. Okay, distance between x and A should be less than epsilon is what it says. Yeah. In other words, this simply says, see, this is B. A belong to Bx epsilon where x is in Q. Have I proved it or not? Yeah? Okay. Now we can do better than that. We can combine both the tricks now. The trick is now, let us look at x minus 1 by n, x plus 1 by n, and x is in Q and n is a natural number. Both look similar, right? Yeah. What is the advantage? See, this collection, this is Vx 1 by n, okay, and this is indexed by x and n. Where do they belong to? They belong to q cross natural number. Now you know this is countable. Whereas our original collection B, which is bxr, okay, that is x comma r belong to r cross r plus. This is uncountable. You see that we bought a very small collection. Okay, then B3 is also a basis. Okay, the proof is exactly similar to using Archimedean property. Okay, how did you show that? The same thing as I did here. Yeah, yeah, this is the trick. Right? Okay, now let's look at other cases. Okay, this is actually two. One is a lot of special cases we looked at. Right? Okay, then the next thing you should understand, okay, this is just a caution, because we use the word basis, and all of you must have seen the word basis in linear algebra. There you think given any vector v, you can write it as a unique linear combination of the basic vectors. This is unique. Okay, so many students may be under the impression here also it's unique. That's not true. For example, in R, let us look at 0 1. This is an open set, right? This open set I can write as 0 half union 1/3 1. Yeah, 0 1 half 1/3. So this and this, right? And both are basic elements. Do you see that? This is already a basic element. These are also elements from the basis, the original basis B. Yeah, and I can also write it as union 1 by n 1 union over n greater than or equal to 2 if you want, and that's also equal to union 0 n minus 1 by n, where n is greater than or equal to 2. Yeah, you see that? So there is no uniqueness. Okay, it's only, you go back to why I am talking about uniqueness. Let's understand. In the definition of topology, I said, yeah, usually people will say any tau open set is the union of subcollection, but this subcollection and the element there may be completely different. Okay, they may not be unique. That's what we saw. Okay, now let's look at example 2 and x tau discrete. This is a discrete metric, discrete topology, right? Now you will see my idea of the simplest open set. What are the simplest open sets containing a given element? Singleton x, right? Therefore, let's look at this. X varies over capital X. This is a basis. So what each bx is singleton x, and x varies over capital X. This is a basis. This is by very definition, right? I don't think it requires any serious verification. Suppose I have x is indiscrete. Can somebody give me a basis? That's very easy, because there is only one non-empty set. Therefore, it should be a singleton x. Is this a basis? Of course. Yeah. Right. Now let us look at our R with a VIP topology. 0 is the VIP. Then we have seen what are the simplest open set containing 0, which is 0, containing any other element x comma 0 if x is not equal to 0. Therefore, what can be the basis? Basis should be, I can simply say x comma 0 as x in R. If I use a set theoretic convention, if x is 0, 0, 0 is same as singleton 0. Do you understand that? Therefore, this is a correct statement. If you don't like it, I will write it like this. Okay, so this is a basis for the VIP topology. So pause, review, proceed. So what should be the next question I should ask? Very good. R with outcast topology. 0 is again outcast. Now what are the simplest open set? If x is not equal to 0, the simplest open sets are x. And if x equal to 0, the simplest open set is all of x. Right? Therefore, what should be the basis for this? Right? Remember, B is a collection of tau. Therefore, I have to say what are the elements coming from here. The elements are singleton x, which are here, and singleton x. Okay, you should not write union x. You understand that? Because these are the things the students should be aware of. Now let's look at R with the lower limit topology. How do you recall how we define lower limit topology? What are the building blocks there? They are the intervals of this kind. Therefore, what do you think should be the basis for this? Note that this is by definition. Okay, the way we define lower limit topology is using these things only, right? When does you say u belong to tau L? For every x in u, there exists a b, so that x belong to a b open, and that's contained in u, right? That's our definition of tau L. Therefore, this is a basis for the topology. Is that clear? Yeah. Can you find something, a smaller collection? How many of you can think of? I should leave this as an exercise, right? This is very easy. But notice that, okay, R plus 1 by n, where R is a rational number, will not be a basis. Okay, we will come to that sometime later, but okay, keep thinking. Now let's look at, there are quite a few things we have seen, and let's look at one more example. Yeah, R with let's say co-countable topology. Is there any basis? Natural basis you can think of? Yeah. See, notice that if I take co-countable topology tau cc, if I take b equal to tau cc, this is already a basis. Okay. So for any given topology, basis always exists. Okay. Whereas in linear algebra, you have to prove the existence. Okay. Don't confuse that basis and this basis. Are you following? Yeah. So there is no question of existence of basis. It always exists. Namely, take this. Like it is something like whether there is a subgroup of a group. Take the group itself, it is a subgroup, like that. Okay. That's not a problem. So basis exists. Now I can ask, just in R with the usual topology, okay, we found that there is a countable collection of a basis, right? I think B3 or B4. Okay, this was R comma, that is bx 1 by n, where x is a rational and n is a natural number. This is a countable collection, right? So there is a basis which is countable. There is a countable basis for R with usual topology. I would like to know R with co-countable topology, does there exist a countable basis? Okay. Suppose B is a countable basis, call it Bn. Okay. Assume, if I do not know whether it exists, but let's assume this is a basis. Then what do I know about Bn complement? Let me call it An. This is countable, right? Therefore, let's look at U equal to union An. This is countable, right? Now let's look at U equal to R minus A. And since this is countable, there always exists an alpha which is an R minus A also, right? Right, this is countable, therefore it cannot be all of R, therefore there exists a number which is outside A. So let me look at now A union this is countable, therefore R minus this set, this is open. Okay, check whether there exists any n so that Bn is contained in U. Okay, suppose you find an x here. Suppose I have an x in U, I have to find an element of the basis, right? That means there is a Bn, so that x belongs to Bn and Bn is contained in U. If that is true, what happens? Then Bn complement, since Bn is contained in U, Bn complement contains U complement, and U complement is A union alpha, right? And Bn complement is, are you following? Bn complement is what? By definition An. So you want to say An contains A. That may very well happen, because what is A? A equal to union An, it may happen. Okay, you understand? You understand this? An may be equal to An because it may be increasing sequence, A1 contained in A2 contained in An, and after that equal to An plus 1, etc. Who knows? It may or may not happen. Okay, so this may happen, but I chose an alpha which is not in A. You see that? Therefore this contradiction shows, okay, there exists no countable basis for R with co-countable topology. Pause, review, proceed. Okay, right. Now just one more example, last example, maybe 6. Let us look at R2, right? Let me look at script B, which is a collection of open AB cross open CD, that is open rectangles. Okay, A less than B and C less than D, A, B, C, D are in R. Is this a basis? Without any work, you should be able to do that. This is what I call armchair thinking. Remember, on R2 we had different topologies, tau 1, tau 2 and tau max. You understand? And what we saw was all these topologies are the same, right? And in a general metric space, we know that for xd, bxr, this open ball, this is a basis, right? Now with respect to the D max, we know the open balls are rectangles. Do you follow that? Therefore this fellow script B is nothing other than, okay, with respect to D max metric, okay, there are some P and R, where P is an R2 and R is positive. Okay, this collection Okay, and this collection are one and the same. Therefore, this is actually a thing. Whereas when I think of R2, usually I think of the Euclidean metric, D2 metric, right? And we define open sets using open disk, open balls with the usual standard Euclidean metric. Are you following? You just want you to be alert. That's all. Okay, so this is more than enough now for the time being. Okay, we have seen a lot of examples. That's good enough. Now, what is its use? Why should I use it? Why should I worry about? I will just do two okay applications or uses. We will see later many such applications. Okay, suppose I want to say X is an adherent point of a set A in a matrix in a topology. Okay, right? Then what should I do according to the definition? Take any open neighborhood U, open neighborhood U of X, then U intersection A is non-empty. This is what I have to prove, right? I'm claiming this is an adherent point of view if and only if, okay, for every B in script B, assuming I'm taking, okay, script B is a basis for whatever be the basis. You fix one basis for all, then I'm going to do that. There for every B in B, so that X belongs to B, we have B intersection A is non-empty. This B is ordinary open set. This B. Okay, is that clear? One way is clear. If it's an adherent point, and since if I take any B which contains X, then B is an open set, right? And B is an open neighborhood of X, therefore B intersection A is non-empty. So this way is clear. Now I have to prove the other way around. What is the other way around? Assume that whenever a basic, usually one calls it a basic open set. Okay, basic open neighborhood of X intersects A. Oh, sorry, not empty. Intersects A. Then I want to show any open neighborhood of X also intersects A. But that's very easy. Why? So this way. Okay, let U be an open neighborhood of X. Okay. Now since B is a basis, okay, and X is in U, I know there exists a B in script B, the basis, so that X belongs to B and B is contained in U, right? Now by assumption, B is a basic open neighborhood of X, therefore B intersection A is not empty. But B intersection A is contained in U intersection A because B is contained in U. Therefore, this is not empty. So I have proved it. You see that? Now what is the advantage? The advantage is I don't have to check for all open neighborhoods. It's enough if we check for very restricted class of open neighborhoods. Right? For example, in the case of R, we saw I only have to look at x minus 1 to x plus 1 by n. Or even in the metric space, this. Right? I don't have to check for all open sets. Do you understand that? Okay. And second thing is the following. Suppose I have a function here from a topological space tau x to a topological space y tau y. Okay, I want to check continuity of f. So what was our mantra? For every v in tau y, f inverse of v, the inverse image belong to tau x. That's an open, right? Now let us assume Py is a basis for tau y. Okay, so I am going to say f is continuous. Okay, if and only if for every b in By, f inverse of b belong to tau x. Notice that I am not talking about a basis for the domain or the domain topology tau x. I am looking at only a basis for the codomain topology tau y. Do you understand this? Okay, one way is clear. What is it? If f is continuous, then you give me any b in by, it's an open set. Therefore, f inverse b must be open in X. Therefore, this is okay. Right? So now let us prove the other way around. So let V be open. Right? Now what is it I have to prove? I want to prove whether f inverse of V is open. Yeah? Now how did I say, what was our important trick, trade secret to prove f inverse V is open? Let X belong to f inverse of V. Then I have to find a Ux, an open neighborhood of X, so that Ux is contained in f inverse V. Do you understand? So that is to prove this. Right? Please, someone, that's why watch my videos carefully. All the important tricks I had already taught, so that it will be easier. Otherwise, again you have to repeat. Is that okay? Very good. Now let's look at, suppose X belong to f inverse V. This implies fx belong to V. Now V is what? Open set. And what do I know? By is a basis. Therefore, there exists a B in By, so that fx belong to By, B, and B is contained in V. This is a basis, and fx belong to V. V is open. Therefore, there is a B. You understand? Now, what is my hypothesis? B is an element of the basis. Therefore, f inverse B belong to tau x. And you follow that? Yeah, right. Now what do I know? Therefore X belong to f inverse B, because fx belong to V. Notice that fx belong to V, and in fact fx belong to B, and B is contained in V. Therefore X belong to f inverse B. Is that okay? Right. Now what is the next I have to do? That's not enough. I have to show f inverse B is contained in f inverse U. F inverse, f inverse B. Are you following? Now start with any Z in f inverse B. That means f is in B. Yeah. But if this implies fz is in V, this implies z is in f inverse V. Are you following? What is that I have to prove? I have to prove this. Yeah. So please pay attention. I want to show f inverse V is open. You gave me an X. Then what do I have to do? I have to find an Ux. What is the Ux? That's what I'm saying. So what do I do? Let us look at fx, that is in V. Therefore there is a basic element in the basis of Y. Therefore fx belong to B. Right? So this is okay. This f inverse B is open. Now this f inverse B is my Ux. Okay, I already know X is here. That's what I showed. Okay. Next I have to show Ux is contained in f inverse B. Right? So that's what I'm trying to show. Start with any z in Ux, that is z in f inverse B. That means fz is in B. That since B is contained in V, fz is in B. That means z is in f inverse B. This is open only. Yeah. So we have shown that X belong to f inverse B, which is in tau of X, and that is contained in f inverse of V. And this is true for all X. In where? In f inverse V. Therefore I have proved f inverse V is open. Please go through that. So what I have shown is to check continuity of f from x tau x to y tau y. What I have to do is, let me write just so that okay, V is in tau y. Okay, this is contained in tau x. Right? This is continuous if only this Now that means for each and every v I would show it. Now what we have shown is f inverse of b, and b is in by. This is containment of x is enough, because by is basis. It's very likely to be a smaller collection, sub collection of tau y. You see that? So basis brings down our work. Okay, we don't have to work too much. That's the advantage. As we go along, we will see a lot more examples. Okay, and let me see whether is there anything which I would like to say. Yeah, there is one more thing which third application. Sorry, I said two applications. I'll give 3 applications. Now suppose x is just a set. Okay, tau 1 and tau 2 are topologies on x. Assume tau 2 is finer than tau 1. Let me assume b1 is a basis for tau 1 and b2 is a basis for tau 2, right? You follow that? So let us go slow. X is a set, tau 1 and tau 2 are topologies on x, and b1 is a basis for tau 1, b2 is a basis for tau 2. Then what I want to say is, I want to characterize, okay, when tau 2 is finer than tau 1 in terms of the basis, in terms of b1 and b2. Is the question clear? Tau 2 is finer if every element of tau 1 is in tau 2. That's very easy. Okay, but as you saw in many of our examples, we defined a topology by starting with a sub collection, right? Some kind of a basic elements, and from that we build the topology. So it will be easier to find a criterion to decide when the topology tau 2 is finer than tau 1 in terms of their basis. Okay, let us assume tau 2, okay, assume tau 2 is finer than tau 1. So what does that mean? Now every element in tau 1 is in tau 2. In particular, let us take any b in b1, then b is in tau 1, that implies b is in tau 2. This is not script b, I'm sorry. Do you accept it? Now since b is in tau 2, what do I know? If you want to call it as b1, so that it will be easier for you to keep track, since now b1 is tau 1, right? Therefore if you give me any x in b1, and since b1 is tau 1, there exists a b2 in the basis b2, so that x belong to b2 and b2 is contained in b1. Have you understood? Okay, if tau 2 is finer than tau 1, start with any b1. Okay, this open in tau 1, therefore it's open in tau 2. Now start with any x in b1. Okay, since b1 is open in tau 2, there is a basic element from tau in b2, therefore there is x b2, so that x belong to b2 and that b2 must be contained in b1. Do you understand? So what we have concluded is the following. Concluded, okay, for any b1 in script b1 and for every x in b1, there exists a b2 in script b2, so that x belong to b2 and b2 is contained in b1. Okay, if tau 2 is finer than tau 1, then this is what we concluded. Do you follow that? So what is the natural question you can ask then? Converse. Okay, assume, okay, this happened. What happens? Assume this happens. b1, okay, I have tau 1, tau 2 b1 b2 with this property. Then what is that I want to conclude? I want to conclude whether tau 2 is smaller than tau 1. Is that clear? To do that, what should I do? Start with any u1 in b1, sorry, u1 in tau 1. I want to know whether u1 is in tau 2. Right? Right. Now let's look at. Now since u1 is tau 1 and b1 is a basis for tau 1. Therefore, given any x in u1, okay, there exists a b1 in b script b1 so that x belongs to b1 and b1 is contained in u1. Is that clear? No. Now what is the assumption about b1 and b2? For any x in b1, there is a b2 so that x belongs to b2 and b2 is contained in b1. Do you understand? Therefore, by hypothesis, there exists a b2 in script b2 so that x belongs to b2 and b2 is contained in b1 but b1 is contained in u1. So what do you think I have proved? I have proved that given u1 in tau 1 and x in u1, there exists a b2 in script b2 so that x belongs to b2 and b2 is contained in u1. So by our trade secret, this means if you want, you call it b2 of x. To show it depends on x, then your u1 is union of b2x as x in u1. But these are all in tau 2, right? Therefore this is in tau 2, that is u1 is an element of tau 2. This means tau 1 is less than or equal to tau 2 or tau 2 is finer than tau 1. Have you understood? Very good. So let us pause, review, proceed. So please go through these things, and these are all actually very easy, but for notation, go through these things. And go through all of these things, and very easy. And once you twice revise, you don't have to remember. You will automatically begin to think very easy, because remember, I already prepared the ground. Where did I prepare the ground? When I want to tell you what is the trade secret of proving some set is open. Okay, so essentially it's a manifestation of that, so you should be easy, right? Do you agree with me? Okay, take care, stay safe, we'll meet again.